Okay, this is number 22 in section 2.2, and the directions say, so a non-homogeneous or non-homogeneous differential equation, a complementary solution y sub c and a particular solution y sub p are given. Find a solution satisfying the given initial conditions. So I went ahead and just I wrote the problem already. So here is our differential equation, and notice it's non-homogeneous, okay, because it's not equal to 0. So in section 2.1, and actually in number 14 that I did earlier, that was a homogeneous differential equation, and this is again non-homogeneous because the right-hand side doesn't vanish to 0. We're also given, right, our initial conditions, and here we're given a y sub c, which they call the complementary solution, and this is actually this guy here we've been working with already. I just haven't called it y sub c. And this is the general solution to the homogeneous equation, differential equation that we've been finding. So we actually, I mean, hopefully the form looks familiar, right? C1 y1 plus C2 y2. And then here we're given a particular solution. So we don't have to find it, but they give us a particular solution. And that's just one particular solution. Here they want us to find a solution that satisfies this specific initial conditions, right? Because this can be a particular solution to different, different initial conditions, right? Because when a differential equation has tons of solutions, right? Infinitely many solutions on the graph. So let's go ahead and start. Okay, so let's use what we know. And let me actually, I mean, there's a lot going on here, so I just want to make sure I define and write a couple things. Okay, so this is obviously a second order linear non-homogeneous differential equation, DE. Okay, we have initial conditions. So what we want to do is we want to use theorem 0.5 in your book. And if you want to look at it, but theorem 0.5, very important, theorem 0.5, it says solutions of non-homogeneous equations. We have a non-homogeneous equation in this case, so that's how I'm using theorem 0.5. And basically, so it talks about why P is a particular solution, right, of the non-homogeneous equation. And they give you the y sub c, and okay, there exists C1, C2, so eventually we have capital Y of X equals, and then we have C1, I write too big, sorry, make this a little bit smaller. Okay, so we have Y sub, Y of X equals, okay, C1, and then we have y1 of x plus c2 y2 of x, right? All the way to the order of the differential equation. So Cn, right, the general solution, Cn yn of x. And then we're going to add this particular solution. So this guy, let's maybe put it in blue, this guy, that's my y sub c. Okay, that's really right here. And this is, again, what we've been finding, our general solution. Again, I just didn't call it y sub c yet, but I mean, we already know how to find the blue. And let's see, let me choose a different color. And then the y sub p, well, I mean, it's given. It's just a nice constant function in this case. It's not always a constant function. So we want to find our capital Y of X. Okay. So we have, so I'm just going to write equals. Well, we already know what y1 of x is, and I mean, in this case, we only go, and our n is 2 in this case, because that's a second order. And we have C1, and then right up here, right, we have e to the 2x plus C2, and then it looks like e to the negative 2x. Right, that's these guys. So e to the negative 2x. And then we have our plus y sub p, and of course our y sub p in this case is just minus 3. Okay, that's our capital Y of x. So this is a general solution. Okay, so important terminology. Okay, this is a general solution, this part, to a homogeneous differential equation. Okay, if we add this particular solution, right, the whole thing, that's a general solution to the non-homogeneous equation. Right, so a non-homogeneous equation always has an associated homogeneous equation. Okay, so let's, well, we need to find our C1 and C2, so we've been doing that by imposition, right? Let's impose our initial conditions, and let me write my initial conditions. I don't have to scroll every time. Let's see, so y of 0 is 0, and y prime of 0 is 10. Okay, so they're my initial conditions. Okay, so we have, okay, so this is the main equation we're going to use. And the book is calling this, this guy, y of x, okay? I'm going to write the same thing, but the book calls it a small y of x, so that's all I'm doing. Now, again, we're going to impose our initial conditions, so I know I'm going to need to take the derivative. So y prime of x, right? And this is just 2c1 e to the 2x minus 2c2 e to the negative 2x, and then derivative of a constant is a constant. Okay, so impose ICs. Y of 0, well, that's C1 e to the 2 times 0 again, which is going to be 0, plus C2 e to the 0, and that's going to give me 0. What does this imply? Well, e to the 0 is 1 from elementary algebra. C1 plus C2. And, oh, I actually forgot my 3 right here, right, because that's not the derivative. So minus 3 equals 0, and we can write that as C1 plus C2 equals C3. Okay, so there's one equation that's going to help us find C1 and C2. And now let's use the second, initial condition. So y prime of 0 is 2. So I'm, again, inputting 0 for x. 2c1 e to the 0, again 2 times 0, minus 2c2 e to the 0, and I believe it was equal to 10, equals 10, again, times 1 times 1, so I get 2c1 minus 2c2 equals 10, and this is nice, we can just divide by 2, so c1 minus c2 equals 5. Okay, so this is where we're going to create there's our system of linear equations, where linear is the Algebra 1 linear, in quotes, definition, not linear in terms of differential equations, but just linear equations, they're lines. So let's construct this guy. Right, and this is ready to go, right? We can use the addition method. So this is 2c1, that's gone, equals 8. So 2 times 4 is 8. So c1 is 4. And if you substitute it back, right, into the equation, right, for any one, c2 is going to be negative 1, right? I mean, 4 minus 1 is 3, or 4 minus a minus 1, which is 4 plus 1 is 5. Okay, so we found our C1 and C2 pretty much done. Now we're just going to rewrite this guy. Hence, y sub p of x, right? Because again, we wanted a particular solution with this specific initial condition. That y sub p equals to -3 is another solution to the differential equation with a different given initial condition. It happens to be a horizontal line. But here we have what was our y sub c, or oh, let me just scroll back up. Okay, so we had let's see, where was it at? Okay, so let's see, let me get, let's see, what color did I use? What color did I use? Okay, blue, so I can be consistent here. Okay, so I'm looking at that, which is really, which is really that, right? And where we're trying to find our C1 and C2, right? So our capital Y. But now we have a solution with C1 and C2. So go back up. And so C1, which in this case is 4, e to the 2x minus e to the 2x, because C1 is -1, and then minus our particular solution. So this is our y sub c, right, with our coefficients. And then again, that's that. This is another, oh, I don't want to do it in blue, right? Right, this is another particular solution, right, with a different initial condition. So that is your answer. Hopefully that makes sense. When we get to 2.3, it's hopefully going to make more sense. Just again, we're going to be covering more theorems, and hopefully you kind of see the big puzzle. Right now we're just kind of connecting the pieces together.